He is from the Physics and Astronomy department at the University of Rochester. And he's also the Stephen Biggar 92 and Elizabeth Azaro 92 Fellow in Data Science. And I've met Gourab because we have a joint project to apply complex systems modeling to a bunch of questions which are interesting in astrobiology and some other topics. So, so I enjoyed a lot our conversations. He's a real expert in complex systems applied to a wide variety of problems that include network theory and you know, the spread of languages in Europe, as you'll find. And today he's going to talk to us about applying this sort of mechanisms and formalism to the study of urban systems. Now, he has joint appointments at the Department of Computer Science and Mathematics, as well as Physics and Astronomy. He was a postdoc at Harvard, where he worked at the Department of Earth and Planetary Sciences in the Multidisciplinary Origins of Life Initiative, which we actually should have one, but we don't. So he got his bachelor's and master's degrees at the University of London. He did his PhD at the University of Michigan. And then he went for a postdoctoral, as a postdoctoral scientist to Northeastern and the Harvard Medical School, and then a visiting scientist at the Media Lab at MIT. So he's had a lot of appointments. Just by his appointments, you can see the breadth of his knowledge. And we're really, really happy to be hosting him today to talk to us about the application of complex systems to urban problems. So Gourab, welcome.
Thank you very much, Marcelo. That was a very kind introduction, probably exaggerated, but I'll take it. So thank you very much for having me here. I would have loved to be there in person. I heard like Dartmouth has a beautiful campus, but things are such as they are, and I hope that that would change in the future so I can actually come and physically meet all of you. So today I thought I'll tell you a little bit about some of the work I've been doing in recent times with respect to urban systems. And before sort of digging deeper into that, just to give you an overview of what I do, broadly speaking, I work in the field of complex systems, which is a very, it's an overarching term, an umbrella term for various kinds of things. But one way of thinking about complex systems is these are systems that are made up of many, many interconnected parts, such that the overall behavior of the system cannot be decomposed by looking at each of the individual parts, which means that these individual parts interact in some kind of a nonlinear fashion. If it was a linear fashion, there would just be many, many copies of the same thing. And therefore, what you see globally is what you see locally as well. But this is not the case over here. Here you have things that are connected to each other. They interact in some non-trivial ways such that if you look at the behavior of the whole system, you can't really sort of decompose that and reduce it down to what the individual components are. I mean, a financial market, for example, is a great example of a complex system. The market exists because you have buyers and traders selling goods. You cannot have a market if you have one sort of buyer and no trader and so on and so forth. So it is the interaction of the buyer and the trader which makes the system work. That is the definition of the complex system. And as we know from personal experience, it's impossible to predict the market based on the actions of individual buyers and sellers. The events of the last week with GameStop and other things, I think is a testament to that. So complex systems, everything, right? Society, the human brain, financial markets, all of those things. But I guess the main thing is that, the interconnected part of it and the fact that they interact in a nonlinear fashion. So the interconnected part of it then sort of brings me to the whole idea of what are called complex networks, which is one of the ingredients of what a complex system. And so I should say something about what a network is. A network is a very, very simple object, allegedly, and it's really just a bunch of dots joined together by lines. In the jargon of the field, the dots are called nodes or vertices, and the lines are called edges. So this is, of course, the most canonical representation. These vertices and edges can have different attributes. They can have more complex structures. They can be of varying sizes, you name it, right? You can go crazy with this. So why do we care about these networks is because, this is after all a representation of things in the real world. It is one way of representing things in the real world. And once you represent things as networks, you may discover knowledge about the system that you would not have if you had not thought about it as a network. It's really the whole idea of going, from these local pairwise interactions to this sort of global interaction, right? So how the network as a whole behaves usually cannot be decomposed into what's happening with an individual node or an edge. And of course, networks, exist, everywhere. And here are some just examples. This is perhaps the most famous example of a network, which is a social network. Here, these dots are people, and the connection between them is if they claim that they're friends. And here's a kind of a geographic representation of the most famous social network of them all, Facebook. So while social networks are, of course, good examples of networks, there are also other examples, and infrastructure networks are particularly important. So this is an example of an infrastructure network, specifically the highway network of the United States. Here, the edges are actual streets, physical streets embedded in some space, whereas in the previous case, there is no notion of space, right? A person sitting at a computer and then having a virtual link, there is no embedding. This is actually embedded in space. It has a metric. So the edges are roads, and the nodes here are basically when two roads cross intersections. So it's a pretty important network, right? Otherwise, you won't be able to traverse the country if it wasn't there. But of course, it's static, and there are other examples of infrastructure networks. And here is a pretty video done by Aaron Koblin, and this is the network of flights, specifically in the United States from North America. And as you can see, it's not just some static, thing which doesn't change. It is constantly changing, and of course, it has a temporal effect, right? So here you see, if you look at the bottom right corner, it's starting to get morning in the East Coast, and therefore the sun rises, and you have flights starting there, and then as time goes on, the sun goes all the way to the West Coast. And then now you have flights from California and Washington and whatnot. And then eventually sort of like Hawaii and other places, the European flights come into play, right? So lest you think that networks are some static kind of thing, I just want, with this particular example, I wanted to just give the impression that, they're actually dynamic in many cases. So here are two examples of infrastructure networks. There are also other kinds of networks. This is a network of, this is what you would call an ecological network. This is an actual food web in Little Rock Lake in Wisconsin. This is data gathered by Neo Martinez and Rich Williams at Berkeley. And here the nodes, the dots, correspond to species. And there is a connection from one species to the other if one species eats the other species. So in fact, these are actually organized in terms of what are called trophic levels. So at the very top, you have sort of the apex predator, if you will, the white-mouthed sea bass. And at the bottom, you have sort of the microorganisms and whatnot. In some sense, you can think of this as an energy diagram. It's a flow of energy, right? So at the bottom is you have the source, and then the energy sort of flows up the network. Here's something that might pique your curiosity, which you have not seen in previous cases. Networks are allowed to have what are called self-edges or self-loops. In this particular case, a self-loop would mean that one species eats itself. So it turns out that the white-mouthed sea bass actually eats its own young. So this is an example of visual representation of cannibalism, if you will. So you have social networks, infrastructure networks, ecological networks, biological networks. Perhaps some of the more famous ones are these, what I would call information networks. And this is, of course, a very small sort of cartoon of what we know as the World Wide Web. Here, the nodes are web pages, and there is a connection between them if there is a hyperlink between one to the other. This is, of course, a very small sample because, in principle, the web is infinite in size. But many things, of course, happen on the web. So this is a network that is of particular interest to people in the field because it encompasses a lot of things. The social technological aspects are all folded into this platform. And the web must not be confused with the internet. Although these two terms are kind of used interchangeably in the common parlance, they're actually quite different. While the web is a virtual network, information network of web pages and hyperlinks, the internet is actually a physical network of computers and routers, right? So this is a representation of the internet at what's called the autonomous systems level. And here the nodes, although you can't really see them because of the size, this is basically of the order of billions. are computers and routers, and the edges are, of course, physical communication lines that can actually break, unlike the World Wide Web. And then my motivation for showing this particular picture is that, it kind of gives you an idea of why people study networks. Because if you stare at this long enough, you see structure. You see kind of these filamentary-like things. You see sort of these fan-like objects. You see kind of this hub-spoke feature, and a variety of other things. So this structure, then of course allows us to ask many questions and answer them. Like, is there any sort of weaknesses in the network? And if there are weaknesses there, can we shore it up? Are there transmission issues? And if so, can we increase bandwidth? Is this design particularly good or for communication purposes? How will it evolve in the future? A variety of things, right? So, so this is basically why people kind of study networks, because, they exist pretty much everywhere. And, this global level information sort of gives you additional insight. But all of this that I showed is to motivate the real question that I want to ask. And I want to motivate that with this particular picture here. So this is, of course, like a nighttime image of North America and Central America. And what you notice is that there are these concentrations of light everywhere, right? And these concentrations of light are there because this is where people congregate together. This is where they live. These are the so-called urban areas. Why do we care about these urban areas? Well, first of all, these urban areas encompass all the networks that I told you about before, right? The ecological, the biological, the technical, the information, all that kind of stuff. Everything resides within these urban areas. And the reason why it's an interesting question is that recently, about like 5 or 6 years ago, we crossed this critical threshold where now over half the world's people are living in cities, right? So here's a graph from the United Nations, broken up across various regions of the world, the various continents. So you see, sort of 1990 and then projections onto 2050. So in North America, the situation is fairly saturated, as even as early as 1990, about 3/4 of people were already living in cities, and but of course there's still room for growth. And by 2050, one would project close to 90% will be the case. A similar feature is seen in Latin America and Europe, Oceania, if you will. But the real growth is here in Asia and Africa, where most of the world's people live. Only about 32% of people were living in urban areas in 1990, whereas by 2050, that'll be 64%. And like I said, so double. Since that's where most of the world's people live, that's a massive increase, right? That's a huge increase. It's almost exponential growth, and it's something which is unprecedented, something we haven't seen before in human history. This whole idea of like people getting together and living in this cramped kind of area, right? So the thing is that this phenomenon of urbanization being relatively recent in historical terms is not entirely well understood, but one needs to understand it because in some sense, it is very much sort of to do with our survival as a species to begin with, because one can ask the question, why do we even have cities to begin with, right? It's not an obvious answer. This whole notion of people living in these cramped congregations has many, many disadvantages. I mean, that we're experiencing right now. I mean, for example, the chances of epidemics spreading and then exploding through the population. There is ideas of resource constraints, shortage of water, shortage of land use, expensive rent. There's the possibility of crime, inequality, all these kinds of things. But of course, allied against that are the good things. So of course, there is the existence of culture, existence of opportunities, sort of so-called nice places to live. So there are these two things, which are these competing tensions, if you will. Somehow they have, conspired against each other such that it is really arguing for one side more than the other. So cities are here to stay, and we need to understand why, how, because really at the end of the day, what we want to do is we want to build a sustainable enterprise, right? We don't want a situation where we put people together in one location and everything falls apart, and then that doesn't really serve any purpose. What we really want to do is sort of, find some balance in terms of like having even allocation of resources, equitable conditions for living, and sustainable living in some sense, such that we're in balance with the environment, simply because if we don't, we'll collapse. And this is a very interesting book by Anne Rademacher, which cities the first 6,000 years, which kind of discusses many of these aspects. So certainly from a historical point of view, if you want to sort of, learn a little bit about this, I'd recommend this book. And I just want to point out that, again, it's not obvious that we have cities simply because in the United States, we have the concepts of suburbs and exurbs, right? And the whole idea of suburbs and exurbs came about because of a variety of reasons, socioeconomic, racial, whatever it is. But in the 50s and 60s and 70s, many people actually left cities and moved outwards, which is why you have this phenomenon. Be that as it may, so I kind of give you these hand-waving arguments for what makes cities good and what makes cities bad. But the reason why I got interested in it is about 15 years ago, we had kind of the first, I suppose, beyond hand-waving quantitative evidence for the things that I said, at least evidence that a physicist will understand. Let's put it that way. So this is a paper by Louis Betancourt and company, who were at the time in Los Alamos, actually all high energy physicists, believe it or not. And what they did was interesting. So at the time, they collected what I would call, let's say, coarse-grained population level indicators of a city, right? So not the micro details, but population level details. So for example, in terms of creative output, in terms of number of patents, employment in research and development fields, the total wages in a particular city, bank deposits, of course, the GDP, but also infrastructure like the total consumption of electricity, epidemic things like the number of HIV cases, the prevalence of serious crimes and whatnot. So what they did was something very simple. They took these things, and since these are population level indicators, they plotted them in function of the population. And when you do that, something very interesting emerges. So here's a graph which plots some of these things that I just mentioned. So crime, GDP, income, and patents. And what you notice first that it's a straight line, and it's a straight line in a logarithmic scale, which means it has this power law form. So it has a power law form of the following. So you have the indicator, whatever one of these things, goes as a population to some exponent, right? The interesting thing about this is that the exponent is not linear, so it's not 1. It's not sublinear, so less than 1, which means you have saturation effects. It's superlinear. So across these wide variety of indicators, you find that this exponent is greater than 1. That's an important thing, and it's in this narrow range. So what does it mean? So what that means is you have these multiplier effects, right? Which this is really the first evidence is that, people say you put people together and good things happen, but exactly in what way does it happen? So what this suggests is that, you have this multiplier effect, this nonlinear effect, where, roughly you double the population size, the GDP goes up by 15%, right? So in some sense. So this is, it's kind of the first real evidence for these multiplier and nonlinear effects of like the interaction among people. And it's notable that, that across a wide variety of measures, it's somewhat similar. And the other interesting thing is that, this evidence can be found in most cities in the world, specifically those who are part of the OECD, who are somewhat developed, which is remarkable because these cities are in different parts of the world. The population characteristics are very different. They have different histories, they have different cultures. They have different geographies. They have different levels of infrastructure in some sense, different political philosophies. But despite all of that, you find this commonality where really these indicators has this quote unquote universal behavior. So why might that be the case? So why is it that all these other factors somehow are not showing up in this, again, coarse-grained measure? So a bunch of colleagues of mine and I, at the time when I was at MIT, we kind of said the following. We said, well, what's common about all of these places beyond anything else is that they have people, right? So a city might have infrastructure, might have all these other kinds of things, but fundamentally it's a collection of people. So if you recognize, as William Shakespeare did in the tragedy of Coriolanus, what is a city but the people, then you sort of throw all these other features away and you just say, fine, why don't we consider that we have some space, there are some population density, and we come up with some way of explaining how these cities might form. And that's pretty much what we did. It was a very, very simple model. So we said, okay, you imagine you have this flat two-dimensional Euclidean space. You see populations randomly or in some other fashion, some Gaussian distribution, whatever it is. And then you define rules in terms of how people might navigate this space and how they might actually form ties with each other. It could be based on proximity. It could be based on some proximity modulated by the population density itself. I don't want to get too much into the details, but really it's just a It's a spatial network model of tie formation based on population density and proximity. So what happens is once you do that, it's you get these sort of interesting, like, these fake city networks. And if you simulate information diffusion on them as a proxy for these, for what leads to the things that I just mentioned before, then you find something which is quite nice. You find that this coarse grain level indicator goes as, the population times a correction term, n log n. So n log n is actually very, very simple, very similar to, like, that n to the beta, with beta having, this very tightly bound range. Just theoretically speaking, it's a cleaner thing, but really that's not the point. The point is that, if the observation is that if you put people together, you get these nonlinear effects, then a mechanistic model that does precisely the same can reproduce this particular effect. So that was satisfactory. So that was nice. So at least that part of it was taken, of course, but it's way too simple, right? I mean, people always mock physicists having, this what's called the spherical cow model. This is as spherical cow as it gets, and there are issues with it. So in this particular formulation, you put people together, you don't allow them to sort of be dynamic. So there is no way in which they can reshape links. And of course, the links themselves are treated in this homogeneous fashion. It doesn't account for the various ways people interact, from a familial to a business to entertainment perspective. But the biggest critique is that the predictions of the model fail when you compare the data. It works in a place like Tokyo, which is well developed, but it doesn't work in some, in more underdeveloped places, right? So this multiplier effect that you're seeing as a function of putting people together exists in some set of cities, again, those that are developed, and not so much in other sets of cities that are slightly poorer and have like less infrastructure, right? So then one has to sort of like go beyond this simple formulation and peel the layers away. Right. So, you start off by saying, okay, fine, it's putting people together is what makes all this happen. We can explain some part of it, but then now we got to dig a little bit deep. So it's like you're peeling the layers of the onion away. And that's really what I want to do in the rest of the talk. So I want to approach this whole idea of understanding urban systems by progressively going deeper and deeper into the core of the onion, if you will, by sort of like, by adding on and see where that gets us. So the first thing that you might think of is, okay, so maybe the reason why in some of these places where you're not seeing the multiplier effect is because people are not being put together, perhaps because they can't get from one part to the other, right? So, there are no roads, whatever it is. So, these are the dynamics, but as we know in physics, the question is like, what is the underlying lattice? What is it that mediates the dynamics, interactions between the people? And of course, several things do, right? But to a good first approximation, one of the fundamental things that allows people to navigate a city and then meet each other is the city streets. So here is an example of these streets. These are like 1 square mile samples. Yeah.
Before you move on, I have a question from someone that says, what is the variable whose growth is indicated by n log n? N is the number of people, right?
N is a number of people, right? And the variable y of t, I believe, is what the individual is asking, is any one of the population level indicators, right? Which is a function of the population. So GDP or wages or bank deposits or infrastructure or epidemic cases or whatnot. So
the same person asked before in your previous picture why there were 3 GDP indicators.
Oh, these are 3. That's a good question. So this is the GDP indicators from different subsets of cities. Okay. That they found, right? So one was Latin America, one was North America, and one was Europe, as far as I understand from that paper.
Okay, thanks.
Yeah. So here are these 1 square mile samples of streets from pretty much different parts of the world, and just visually looking at them, you see variation, right? You see New York has this grid-like structure, so does Toronto. San Francisco has a mix of like anisotropic grids in some sense. Rome is more chaotic. London has its own sort of like, thing. So, just looking at these 1 square mile samples, you might say, fine, these kind of street layouts in different parts of the world are quite different. So perhaps if one were to study the structure of these streets, then one might explain why in some cases you get this multiplier effect, in some cases you don't. So at least that's a hope, right? There are many, many things that one can study about these streets, structurally speaking. But if it is connectivity that we are interested in, a natural thing to study would be a level of congestion. So are there bottlenecks in the streets where sort of like, people, things get stuck, so you can't go from one part to the other? There is this concept in graph theory called the betweenness centrality, which measures this level of congestion. And very simply speaking, here is this toy network. You have some region over here and some region over here. Just by looking at this, you can see that this particular vertex A has a high amount of congestion because it lies on all possible paths between these two different parts of the network. So very roughly speaking, that's all the betweenness centrality is, right? It's measuring how central is a particular node in the network as a function of how much it lies between paths of any other parts of the network. And those paths could be of any type. It could be the shortest paths, the fastest paths, if there are like speed limits. It could be the most scenic paths, if you will. It doesn't make a difference how you define the path. But essentially, it's a measure of congestion depending on the process that you're trying to think, right? So one thing one could do is we go to all these cities, we do a histogram of the congestion on these streets and say, well, are there differences in the histograms? And perhaps that might give us some insight. And it was actually done about 2015 years ago now. It was a very nice paper by Vito Latorre and company, where the computational power and the data sources weren't so great back then. What they did was they literally sort of hand transcribed these street maps from an actual book, entered into a computer program, and then reconstructed the streets. Naturally, that's quite intensive and takes a lot of time. So these samples weren't huge. These are these 1 square mile samples. This is specifically Venice, and these pictures refer to different measures of centrality. This is the betweenness centrality, the measure of congestion. So you can see sort of like along the river Arno is where you have not the Arno, but the other river. You have sort of these high traffic streets. But more importantly, what they did was when they plotted the histogram. Again, you take a node, you measure the congestion, and you just create a histogram. When you plot the histogram of different cities, they claim that they were able to find differences in the tails of the distributions, and there was a connection made between whether a city was planned, like Los Angeles or Richmond, or where it grew more organically, like Cairo or other places. So my group and I were working on a different paper, and we also dealing with streets, but we happen to have a much larger data set because, of course, it was about 12 years later. There's something called the OpenStreetMap API, where you can just run a query and get the street networks and routes of pretty much any city on the planet. So we looked at sort of the 100 most populous cities. And unlike these 1 square mile samples, we collected pretty much the entire city. So the order of 3,000 square miles in this particular paper. And then we said, okay, let's plot the histogram of all these particular streets and see of congestion, and then see if we can learn something from it. So this is what it looks like. So the previous plot that I showed you was these small samples. And this is, of course, a level of the entire city. And you find this kind of strange looking shape. Again, this is a log scale. The vertical axis is a fraction of roads that have that level of congestion. But anyway, what you see is these two different behavioral regimes. You have kind of this weird kink in the middle, and you have these long tails. What's interesting is that if you account for the actual size of the city, in other words, the number of roads, and you rescale the distribution, then it looks a lot cleaner. So in other words, all of these peaks kind of line up, and you can clearly see these two different regimes where you have this kink, and then you have some noise over here, and then you have these long tails. And furthermore, if you account for not just the size of the city, but the actual shape of the city in terms of its morphology in some fashion, there's another level of rescaling. Then you look at the distribution of congestion, and it looks pretty much exactly the same everywhere. So again, that's quite remarkable, just as in the scaling behavior that I showed you before. So just to say, so the reason why you have these two different behaviors is kind of technical point, but every street network has a backbone. That backbone is called the minimal spanning tree. And the minimal spanning tree carries most of the load and congestion. And the rest of it pretty much comes from the loops. So every time you connect parts of a tree, you get a loop. So that's not really the interesting part. All the information is in the tree. But whatever, the point is that this is, it's kind of strange saying that if I look at the street networks of pretty much any city in the world, and I account for the system size and I account for the shape, then the distribution of congestion is exactly the same, which means it's a fairly useless piece of information, right? It doesn't tell you anything about how to distinguish between cities. It certainly doesn't jive with the intuition that we had before, which is perhaps if I study congestion, I might be able to explain the differences between those cities where the connectivity is low, where you can't get people together, and those where they are sort of like, where they're seamlessly connected. The interesting thing is the information is not in the distribution of congestion, but actually in its spatial layout. So here is what's happening. So on the right-hand side is an actual city. This is Santiago de Compostela in Spain. That's the street network. And you have the ones that are lit up in these lighter colors are the ones are parts of the city that have the highest amount of congestion, the highest amount of traffic. On the left-hand side, you have, again, without getting too much into details, a random graph, a simulated version of Santiago through some model that we have. And we are showing, once again, the parts of that street network with the highest amount of congestion, the top 10% in this case. And these are colored in red. And so if you look at the structure of it, you see it's kind of this winding, tree-like structure. There's no interlinking and whatnot. And the thing to note is that there is a control parameter here, which is a density. So in other words, this is a measure of the number of streets that actually exist in Santiago versus the total number of, divided by the total number of streets that can exist based on the spatial constraints. In other words, Santiago is a relatively sparse street network. But if one were to go to networks with higher density, so here's Paris on the right-hand side, and you can see the difference here. Here you have this kind of this tree-like thing, and here you have this interlocking web-like structure, and the same thing in the fake version of Paris. And the other thing is that you see is that from here to here, they start to coalesce towards the middle. If you go to cities with even higher amount of density, this is Shenyang in China, then you see that that interlocking structure is now really just a clump in the middle, right? So you go from here, tree-like, to this interlocking thing, to the clump-like structure. So what this is saying is that there is actually some interesting information in the distribution of congestion in the streets, but it's not really in the histogram, it's in the spatial layout. So it turns out that, naively one might think that if I'm starting as an urban planner, that I want to connect various parts of the city, the naive thing to do is to build as many streets as possible. While building as many streets as possible is nice, but there is a payoff, and the payoff is that for geometric reasons, it turns out that irrespective of what kind of paths you look at, all the traffic gets coalesced more and more into the central part of the city. So you're connecting people, but you're creating this bottleneck. And the more you create this bottleneck, the more you make it difficult for people to navigate different parts of the city. So actually, there is some interesting information about, in looking at, how these streets are laid out. They are playing a role in how people are connected or not in this kind of non-trivial fashion. And you actually see this in actual policy, in real policy. So in New York City, you might be familiar that they closed Broadway a while ago. And the reason why they closed Broadway was they thought that based on numerical simulations, that it would improve the traffic, right? You would have like higher throughput between various parts of New York. Whether that's true or not is a debatable point, but that was the thinking behind this. There's also another policy that's being used, it was being used in Singapore for a long time, now in Stockholm and London, and now recently in Manhattan, what's called congestion pricing. So congestion pricing is an active economic disincentive for you to drive your car to the central part of the city. In other words, if you were to try to go to downtown Manhattan or whatever, Midtown or whatever it is, you would actually pay a toll. Singapore has been doing this for a long time. So effectively what you're doing by closing streets and then creating a disincentive to actually drive your car to the streets is you are lowering the density of the streets, right? So as you lower the density, you see that you go from this congested center and then things kind of spread out. So this is kind of a nice theoretical reason for why one would actually follow a policy like this. But really the answer is not so to blindly sort of build infrastructure, to build it in a smart way. You could build multimodal infrastructure. You can be clever on how you connect the different parts of the city. You can be clever in terms of how you have land use and whatnot. And there are many, many other things that one can say, but I would rather sort of just move on briefly. I've already spoken quite a bit. I haven't even got halfway through. So the first part was you put people together. The second part was you say, all right, what is it that mediates interaction? And then the third part is that how do people move? So this brings me to a very exciting kind of like development over the last few years, well, last decade or so, is like models of human movement. Now, I must say that one can always construct any kind of model one should choose, but the only way one can check whether the model makes any sense is to have the data. And so phenomenological modeling is what I mean, really. So it turns out that that data is now recently available. And one of the sources of such data is these mobile phone data. So here are two snapshots of the same individual traversing various parts of a region. The dots correspond to the location, and the edges correspond to the fact that, those locations was connected by a trip. So how it works is, I make a phone call, I ping a cell phone tower, in some space. Then I go somewhere else and make another phone call and I ping a cell phone tower. Then I go to another place and make another phone call, I ping a third cell phone tower. And as often as I do this, I have this trajectory of moves, right? And just by looking at it, maybe there's no information here. It looks like a mess, right? So this is one person, this is the other person. All you can say is that this person is far more active, makes more phone calls. This person makes less phone calls. Is there any structure here? It turns out there is a very regular structure here. If one were to plot the displacements, right? So the distribution of the typical distance of a trip, that's this thing over here, you find this very regular form. It's called a truncated levy distribution, right? So you have this, like a levy flight from random walks. So you have this power law thing, but you have an exponential cutoff. This idea about levy flights in terms of movement is not a new thing. It was actually being applied in terms of looking at the migration behavior of birds. And then I guess it was reasonably exciting to see that the same distribution or the same form or the same mechanism also applies to human beings. But there's a problem. The problem is the following, is that if human beings were really random walkers, whether they're doing a Brownian, a regular random walk or a levy flight, there's something called the mean square displacement, right? So eventually, if you had a levy flight, whatever it is, you would diffuse away to infinity, right? So you start from home, you go to work, you go to a coffee shop, and then as time goes on, the theory suggests that you will drift away to the ends of the universe. But that doesn't happen. What happens is we actually go back home, which means that there's regular behavior. And one can measure this by looking at what's called the radius of gyration, which means what is the characteristic distance that the typical individual moves. And that has some cutoffs, which means that human beings operate at characteristic length scales, right? So we move up to a certain distance, but not much beyond. So when you combine these two things, what you get is what's called ultra slow diffusion, which means that your displacement is a log of a log, which means that really for practical purposes, you don't move beyond a particular time scale. Either way, so all that is nice. I think what's remarkable is that, that you can actually, that human sort of movement behavior is actually very, very regular. I mean, we like to believe that we are sort of all unique and everything, but it turns out that we are all extremely predictable. One thing I won't talk about is you can take this information and feed it into information theoretic framework, and you can make statements about how predictable human beings' movements are. In other words, if I were to observe your past behavior, how likely am I to guess where your next location is going to be? And the answer is 97%. So, and all of that comes from basically this regularity in this behavior. Okay, so that's great, but I want to illustrate a point with this. So you see, this is data that's taken from cell phones. The problem with the cell phone data is that you're not constantly making calls, so there's no fine resolution in terms of your movement. And secondly, these are instantaneous displacements, right? So I make a phone call in one zip code, then I jump to another zip code, and I make another phone call. So it's like a straight line from there. So there's a lot of information that's missing from this particular data. So some colleagues and I got access to GPS data from an insurance company in Italy, and this covers about 2% of traffic in Italy over a 1-month period. There are many cars and there are many trips. On the right-hand side is kind of like a visualization of the density of traffic. And in addition to this displacements, now you have information about not just the displacement, but also the velocities, the typical velocities, the travel time from one location to the other, as well as the amount of time that is spent, the waiting time, so-called, the rest times. So with this additional information, what can one do? Here's a distribution of the typical time of travel in a semi-logarithmic scale for these different cities in Italy. And they all collapse nicely into one curve once you divide it up by the average time it takes. All this means is that these are exponential times, right? So the typical distance, the typical time it takes to go somewhere sort of decays exponentially. In other words, one doesn't, there are very few trips that take a lot of time. Most of them take a reasonably small amount of time as compared to the average. So unlike the previous case, what you can do is you come up with this really kind of, I would say some stupid model, in fact, in some sense. You just say that the velocity is just a random variable. So here you have the V dot goes as some diffusion coefficient times some white noise. And you can calculate the displacements accordingly. And then if you combine this with this observation of exponential travel time, you get a prediction for the displacements, which has this particular form. The only thing I want to illustrate with this is that this form is not that truncated levy. It's in fact like, it's a different form with it's really what's called a stressed exponential, right? So it's very different from what you get by looking at the mobile phone data set. Moreover, you can also predict that the average velocity in time sort of goes as a square root of t. But unfortunately, when you sort of plot that on, look at the actual data, you see that the dependence between the velocity and time is more a linear function, and it's not this square root of t, right? So obviously, once again, this model is way too simple to explain what's really happening. But it turns out with a small refinement, it does a pretty good job. And what is that refinement? It's the following, is that you just make the observation is that, when you typically go to make a trip, you start off in your garage, you have some velocity, then you go into your side street, you have some velocity, then you go from your side street to a main street, your velocity increases, and perhaps you go from your main street to the highway where the velocity maximizes, but then you take an exit, so the velocity goes down, and then as you get to your destination, slowly and slowly your velocity goes down, down, and down, right? So there's a hierarchy of streets which governs your velocity profile. So if you just take into account this particular hierarchy, you just say, okay, there is some typical interval in which I change my velocity, and you have these stochastic kicks. And the fact of the matter is that, as I halfway through my trip, I reach maximum velocity, and then as I get to the end, my velocity goes down. Again, very simple model, right? It's just random velocity with this hierarchy. Then it turns out that you get this prediction of the velocity going linear in time to be perfect. Moreover, matches. Moreover, the distribution now is a slightly more complicated thing. However, it does match the observation in the data quite well, right? So this is the actual data of displacements of cars in Italy, and this red line is the prediction. So this simple model of random velocity fields operating in this hierarchy actually does a fairly good job of explaining what's happening in traffic in Italy. The point I want to illustrate with this is that this is the challenges that we face as a community who are working in this field, because you see, there is a certain amount of things that one can get from one data source, which is cell phones, that you have this heavy tail distribution, but it's this truncated levy, which has its own problems. And then you get another data set which deals with GPS, and you have a slightly different prediction. So the question is, one doesn't really know for sure which one is right, but hopefully, as you sort of peel the layers of the onion, you're getting closer and closer to the right answer. But at the end of the day, the thing is you need more and more data. Okay, so we've had the people putting together, we've had the streets, we had the models of human movement. Now, what happens when you put the movement together with the infrastructure? How do they sort of talk to each other in some sense? And this brings me to this idea of what we call structure of dynamic interactions. But just very simply, let me put it this way. So here, this is data that we have from a collaboration of my group and others in Europe with Google AI. So, Google, of course, has information about people's movement from Google Maps, but also from, IP searches and whatnot. So what they did was they collected the information about like 300 million people from all over the world. And of course, they aggregated that. They made it anonymized. There's no individual level information whatsoever. It's only population level information. And what you have is mobility flows, right? So you say, okay, from pretty much any part of the world, from one zip code to the other zip code, how many people moved between these zip codes for some period of time, let's say a week. So that's what this is showing in the upper left corner for the United States with New York City as inset. The dots are locations, the lines are the population flows between these areas, and this is the intensity of the flow. So what you can do is you can do something quite interesting with this. Here are examples of like 6 different cities from all over the world. So the way to read this is from left to right. What you can do is you can go in a city, you can measure the amount of flows that goes from one location to the other, and you can apply some kind of a thresholding. So in other words, you can use this notion of Lorentz curves and say, I'm going to separate different parts of the city depending on how much flow actually goes there. So you have a level 1 hotspot meaning these are the areas where most of the people go to. And then you apply the thresholding even more. Excuse me, you get level 2 hotspots, you get level 3 hotspots, you get level 4 hotspots, and so on and so forth. Again, hotspot defined in terms of the part of the city that is visited by the most amount of people. So if you look at it structurally in Paris, you have this core structure, right? You have this real thing in the middle of the city, and then you have progressively, as you go out and out, you have lower amounts of flow. The same thing is true in Alexandria in Egypt. But as you go to Bangkok and Santiago, this is Santiago, Chile, you see it starts to spread out. And as you go to areas like Los Angeles and Sydney, you see that these areas of high location visits are even more spread out. So in some sense, one could say that these are centralized cities. In some, they're central in the sense that most of the economic activity and the population resides in some central part of the city. Whereas these, you could say, are more sprawled cities. And if you're in Los Angeles, it's sprawled, right? There are like 7 different downtowns and all kind of stuff. So what's interesting is you can quantify this level of centralization and sprawl by measuring to what extent the population flows only between the hotspots, only within the hotspots and between the hotspots. So if they flow only within the hotspots, which means only high population centers interact with each other, then you can define this measure phi, it is what, I won't get into details, that's high. So if only high population areas talk to each other, it's a high value. So it's centralized. If you have sort of low population areas and high population areas interacting, so it's more in even democratic fashion, then this particular value is low. So this is, by the way, there's no mechanism or model here. It's a purely observational empirical analysis. But what's interesting is that this particular measure is a proxy for the interaction, is a proxy for the mediation through the infrastructure and the actual population flows. And it turns out there's structure there as well, because some cities have a very high level of interaction between high population areas. Some cities have a very low level of interaction. And if you just were to measure a bunch of transportation, pollution, and health indicators from a city as a function of this level of centralization or sprawl, you see some interesting trends. So you see, for example, in the US cities where we had the most information, if you look at sort of the share of cars that exist, the more centralized the city, the less amount of private transportation is used. Correspondingly, more public transportation is used. Correspondingly, more walkability happens. You have lower emissions of various pollutants for more centralized cities, and correspondingly also lower incidences of health indicators, like sort of like ischemic stroke, traffic fatalities, and all kinds of other things. And the same thing sort of shows up in various parts of the world. So what's interesting about this is that you can essentially, again, from a policymaking perspective, you're taking information that is reasonably easily available, depending on the sources, and you're just taking this sort of like this dynamic structure of the cities in terms of how people actually visit the various parts of the city, and somehow that carries information about the characteristics of a city, specifically things about like the environment, about health, and various transportation modes and whatnot. Okay, I'm already way over time, but I want to end with this important thing because of the current situation. So this, if you're interested, you can look it up. This is a paper, which is Epidemic Spreading. So if I can just go a little bit over time, I just want to go over this very quickly. I don't have to tell you why this is important. We're living this reality right now, right? But one of the main applications of this thing, of the study of mobility and infrastructure and stuff, is understanding precisely how we can understand, how we can prevent the spread of harmful diseases. There are many ways that one can model epidemic spreading. The traditional way is purely a structureless differential equation framework, where you have a set of equations describing the various states of the disease, but otherwise there's no structure. And based on this, you can calculate things like the incidence, the saturation rate, the critical level of infection for the pandemic to take off and whatnot. The other extreme approach is to do what's called agent-based modeling, So this is a hyper-specific simulation of what's happening in a city. A good example of this is EpiSim, which was developed by Los Alamos, where literally, they would go to, they would literally try to simulate exactly what's happening in Dartmouth. So every single individual has some rules on how they're interacting, and then they bump into each other. There's some epidemic rules over there, and you can see how the infection spreads. So it's very, very computationally intensive. So on the one hand, you have something which is analytically tractable, computationally easy, but has no structure. On the other hand, you have something which is a lot of structure, but is computationally very, very hard to do, right? So it's something which is not scalable and something which can't be done in real time if you want to fight a pandemic. So what one can do is split the difference. So splitting the difference leads us to this idea of metapopulations. This is a thing which is kind of actually borrowed from ecology, but roughly speaking is the following. You divide up the world into various patches. You can imagine that each of these patches, let's say, corresponds to an area that's covered by an airport, right? So this is the Newark patch. This is the JFK patch. Within these patches, people reside, and within that patch, you have no structure, right? You assume a fully mean field kind of situation where everyone interacts with everybody. But between the patches, you have this population flows. So as one person goes from this patch to the other patch, they can infect them, they can recover, and they come back, right? So really, it kind of splits the difference between the structureless and the full structure thing into something which is more governable. So I'll just illustrate this with a cartoon. So imagine you have 4 different parts of a city or some region, and each of these has some NI number of people living over here. Then you say that, okay, you have to work or you have to go somewhere to watch a movie or something, so people commute. So you define that there is some parameter, a mobility parameter, which tells you how many fraction of people sort of go from one part to the other. And the moment this is non-zero, you have these flow matrices, flow matrices between locations codified by R. And so you go, you mix, so people from here go over here, they mix over here, mix there. And depending on the epidemic, you might have infections with some rate lambda, you might have some recovery with some rate mu. And after these interactions happen, you go back home, right? This is what's called the movement interaction return model, MIR models. And I've given a very, very simple example of how of epidemiological case. It's just a simple SIS model. You can make this as complicated as possible as you want in terms of the infection parameters. And in fact, the way that people are modeling COVID right now, there's about 37 of these. But the fundamental thing is the following, right? So you have people living in a region. There is some pattern of flow between the regions. They commute, they come back, and the infection sort of spreads. So there are some non-trivial things behind this, which I can probably discuss in the question and answer session. But here's a test case. This is before COVID, by the way. We did this in the city of Cali in Colombia, which is divided up into various regions. These are the actual mobility flows between these different parts of the city taken from the census data. And so you take that and then you feed this into your favorite epidemic model, whether that's the flu, whether it's COVID, whatever it is. And one of the outputs of the model is, the incidence, which is the number of people going infected per capita, as a function of the infection parameter, right? So typically what happens is below a certain value of the infection parameter, nothing really happens. Everything is kind of steady state. And then it's a critical value of the infection parameter, the pandemic takes off, similar to a continuous second order phase transition. What's interesting about this is that we have generated these various curves for varying degrees of mobility. So when P equals 0, the blue curve, that's the critical parameter over there. But then as you switch on this parameter, you allow more and more people to go to different parts of Cali. Now, in a pandemic setting, you'd imagine, or any kind of epidemic spreading setting, you'd imagine that, if people are moving from one part to the other, then that's a bad thing because you're actually spreading the disease all over the place. But it turns out it's not so simple. It's actually non-trivial. So if you were to look at the blue arrow over here, which is no mobility, versus the red arrow over here, which is about 70% of them are moving, you will find that the threshold is higher, which means you need a higher epidemic threshold for the pandemic to take off, right? So it turns out that, again, based on the structure of the city, based on the differences in how the population is located, non-trivial ways to prevent the spreading of epidemics actually is to foster movement as opposed to hinder movement. Again, depending on the particular setting, right? So that was kind of an interesting finding, which was kind of non-intuitive, but if you think about it a little bit deeply, it actually does make sense. So this is something which just came out recently. Again, this is I think January of 2020, right before COVID, and then of course we got to work on COVID. So I won't talk much about that, but just to give you an idea of how people actually study these things. So it's all of those things that I just told you with the model, the movement, interaction, return stuff. You have the street networks, the flight networks. You have your epidemic model depending on the type of the pandemic. You have the mobility data, and you have the population density data. So you kind of layer all of these together, and then you have sort of these ensemble models, which is a combination of these analytically tractable things and then large scale numerical simulations. And these are the kind of things that sort of like people have been using over the last year to simulate and sort of like to project out how the pandemic is going to go. And of course, many of them have several problems, but that could be discussion for some other time. It's already 4 o'clock. I apologize. I've taken up way much of your time. I could have talked a little bit about some specific things about COVID-19, but I rather do it some other time. So I think, thank you very much for your time. I'll just skip through this. Sorry?
I am going to applaud in the name of everybody, and clearly we have to bring you back.
Maybe, yeah.
Because there's so much more that you want to show us that is really interesting. COVID and pattern formation, and that sounds really amazing.
Right. Thank you. So I'll just want to thank my collaborators and of course my group. If you want to know more about what we do, please visit our website here. I also tweeted Ghoshal ji, these are my funding things, and these are my wonderful students and postdocs now who have gone on to do much better things, and really this is most of their work. So thank you.
You're very welcome. Let's see, I'm trying to find Robin here. So I have a question from Robin. Okay, let's see. She's saying, presumably the pandemic altered human movement, characteristic, land scale, etc. Has this been looked at?
Yeah, in great detail, yeah. I mean, so let's see. Maybe this won't illustrate the point. But anyway, so one of the things that people have been doing is, I guess here you can see, right? So I'll give an example. So it's a good thing. So these are 3 different cities in the United States, from left to right, sprawl to centralized. On the vertical axis over here, you have what's called the REffective, which is you have to put it in very simple terms. On average, how many more people can one infected person infect? If the number is greater than 1, you have pandemic. If the number is less than 1, you have things under control. Talking about like how mobility has changed. So here you will see this value, this computed value of REffective from the real infection data, organized here as a function of the amount of flow reduction that we can measure based on the mitigation measures, right? So if you see sort of, this is the week before 100 cases, week of 100 cases, 100 cases, whatever it is, it's a temporal thing. So there's a lot of work that ties up, what this REffective is based as a function of how the mobility changes. And then sort of like people look into it very carefully, et cetera, which changes the complete sort of patterns of the things that I showed you before, and then see how you can mitigate the disease. There's some other interesting things over here, but I'd rather not talk about it because I haven't given the proper context. But yeah, I mean, long answer short, yes, it's studied in great detail.
Okay. Are there any other questions from anyone? Yes, here we go from James. Thank you for the excellent talk. It was fascinating to be reminded what it means to be human. What about non-mechanical aspects of human interaction, i.e. positive, negative, governance, etc.? Are these not an indicative variable in the interactions? So I think he's talking about more like a much harder thing to quantify, I guess.
Yes, and it's a very good point. And perhaps there are ways one can quantify it, but it's not obvious. But one of the reasons, let me just go back to like, March and April when you were seeing all these projections, right? So you had, you had this famous SAGE group from the UK. I think it was Neil Ferguson saying that we're all going to die. There'll be 3 million infections. And if you don't shut down right now, the world is going to end. And then you had other models which said something different. Then you had what's called the IHME model from Washington University, which they're still using for whatever reason. All they're doing is curve fitting. And each of them gives you very, very different answers, right? None of these models actually are bad in themselves, except for the IHME model, which is not a model. It's a curve fitting approach. Where all of them kind of miss things is they can't quite capture the variations in human behavior. They can't quite capture the variations in how different parts of a country would respond to, let's say, a mask mandate. They won't capture sort of the various political aspects. They won't capture sort of some of the mixed messages in policy. The answer is these are, of course, extremely important, but it's very, 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 very hard to quantify and somehow include them in your models. Instead, what one should do is one should be careful in what you say about, one should be careful about prognosticating from your models. And then one could perhaps work out various kinds of scenarios, which would correspond to the behavioral changes, but in some actionable way. So what would this actionable way mean? That would mean that, okay, in certain parts of my region, people just move freely as compared to some other parts of the region where they're actually stay at home. The infection rates in various parts of the regions will vary based on, how much they believe this is a real thing or how much it's a hoax, right? You can't do it for certain, but you can do various kinds of scenario analysis. That's really the best you can do. So
there is a contextual issue too. For example, something that could be positive behavior in one context, for example, oh, let's go watch a hockey game.
Yeah.
Negative behavior
exactly.
in another context.
Absolutely.
So
Absolutely.
it becomes incredibly difficult to do this, but it's a very good question. And
yeah.
Christina, do you want to say that in a live voice? You can now.
There we go. Are you hearing me?
Yeah, we can hear.
Yeah. Thank you. I am interested in the question of comparing maps. Particularly, I'm looking at maps of ionospheric flows and maps of ionospheric currents. And one of the things we struggle with is to say that this model of the flow map is or is not like that model of the flow map. And I'm curious what tools you use to metric or quantify how different or similar various maps or spatial representations of information for your cities are from each other.
Well, it depends. I mean, so there are various things one can do, right? In this particular specific case, it was a reasonably simple measure. It was we first of all used some thresholding method to divide up the city spatially depending on how often they're visited. And then we quantified how the differences based on the level of interaction between these regions of a particular level. That's one way of doing it. The other way, is there are various spatial metrics developed in quantitative geography. One of them is called the Moran's eye. So it's a measure of spatial correlations and spatial order based on a binary variable. Then some of the other things that we could do is look at in terms of the isotropy and the anisotropy of these structures just by looking at the ratio of the eigenvalues of the covariance matrix. So I suppose the answer is there's not really one particular methodology that allows you to compare these maps. It's more a function of exactly what aspect are you comparing, and of course what question you're trying to answer, and then based on that you use the relevant tool. So
thank you.
Yeah. But it should be possible to construct maps based on the data that they have, I imagine. Yeah. Any final questions, comments, anyone? 1, 2, I don't see anything. Okay, well, let's thank Gourab again. So excellent.